Planning a university degree sounds like a straightforward scheduling problem. But if you've ever tried to map out a 4-year plan from scratch, you know the reality. Graduation requirements are scattered across dozens of departmental pages, PDF handbooks, JSON APIs, and HTML catalogs. The logic is deeply nested. You have prerequisites, corequisites, choose 3 of 9 clauses, general education waivers, term-level availability, and workload caps. And if you're using an AI agent to build this plan, you run into a fundamental architectural flaw: circularity. If the agent only visits pages relevant to your current interests or transcript, it will never discover the rules that actually block your path. It plans over a partial graph, misses a hard constraint, and hands you a plan that looks feasible until you try to register. This is exactly the gap the KnowPlan framework addresses. The researchers behind it realized that reliable degree planning isn't a single modeling problem. It's a 2-stage acquisition and optimization pipeline, and the interface between those stages needs to be explicitly measured, not assumed. The solution splits the workflow into 2 strictly isolated components: CatalogBrowse, which extracts the curriculum without ever seeing a student profile, and DegreeMap, which takes only the extracted data and optimizes a personalized plan. No circular dependencies. No biased crawling. Just a clean, verifiable pipeline. Let's start with CatalogBrowse. Its job is to reconstruct the institution's curriculum from a frozen snapshot of official sources. But how does it decide what to crawl and when to stop? Most web agents use a reward function tied to task completion, which encourages them to stop as soon as they find something that looks useful. That's exactly what causes the circularity problem. CatalogBrowse fixes this by defining a finite set of atomic obligations. Discover an official index, instantiate a course entity, fill a required schema field, resolve a typed prerequisite reference, and attach provenance. At every step, the agent evaluates every legal browsing action by its lower confidence, bound on expected marginal obligation gain per unit of source access cost. The lower bound acts as a conservatism device. If an action type has few observed outcomes, the confidence interval is wide, the score is discounted, and the agent prefers evidence it has already validated. It only pays for unfamiliar actions if the obligation itself generates positive expected gain. This keeps the crawler focused on structural coverage, not just surface-level answers. Parsing is handled deterministically first. Platform-specific adapters extract indexes, identifiers, titles, units, and simple relations from APIs, DOMs, PDFs, and structured records. The language model is only invoked against a visible exact span, with a finite clause-to-ASD schema. It cannot hallucinate URLs or course IDs, because the identifier enum is built strictly from tokens present in the span. If validation fails, it retries once with feedback. If it fails again, the field stays unresolved. Crucially, CatalogBrowse doesn't stop based on a learned threshold. It stops when a closure certificate holds. This certificate verifies that every discovered index entry is either bound to an entity or explicitly failed, every schema-required field is present or marked unresolved, every provenance offset lies within bounds on an actually opened page, and the 3 output documents validate. The certificate is snapshot relative, meaning a third party with the same frozen source can recompute every condition from a hash chain trace. It's a hard terminal condition, not a heuristic. Once CatalogBrowse finishes, it emits exactly 3 provenance-linked JSON documents: courses and typed prerequisites, program requirements, and general education frameworks. DegreeMap receives only those documents and a student's profile. It never sees the raw web. The first step is compiling those JSONs into a typed requirement hypergraph. This is where most planners fail. Traditional approaches expand compound requirements like choose 3 of 9 into pairwise clauses, which relaxes the constraint and admits plans no academic advisor would sign. DegreeMap keeps them as atomic hyperedges using all OF, any OF, choose-n, and min-units operators, so the solver enforces the exact cardinality. Personalized utility is calculated per course using a weighted combination. It adds direct semantic interest, typed graph diffusion, prerequisite unlock value, major and GE gains, and future option value. Then it subtracts workload, scheduling risk, and aversion. The diffusion term runs over a typed adjacency where fulfillment and cross-listing edges carry distinct weights, but prerequisite edges carry none. That prevents structural dependencies from leaking into topical relatedness. The unlock term propagates interest backward along prerequisite paths, discounted by distance, and divided among alternatives satisfying the same downstream requirement. Planning itself is handled by a CPSAT solver using lexicographic optimization. The objectives are solved in strict priority order: hard feasibility, minimum completion horizon, load and risk, personalized utility, future option value, and a deterministic tiebreak. Each stage locks in its proven optimum as a hard constraint before the next stage runs. This staged narrowing is what keeps the problem certifiable within a 60-second solver budget. If a plan can't prove optimality in time, it's emitted uncertified and counts as a failure. Top K plans are generated using no-good cuts and Hamming diversity cuts, ensuring alternatives differ in actual scheduling, not just timing. For unknown preferences, DegreeMap uses targeted clarification. It solves under every remaining finite preference hypothesis, and only asks a question when the canonical optimum isn't invariant. It picks the question with the greatest expected regret reduction per unit of interaction cost, then replans. The pipeline was evaluated across a 100-university broad track and a 6-university dense track, with mask source tests that hide index pages to expose entities task-directed crawlers would miss. CatalogBrowse achieves 96.2% inventory recall and 88.7% mask source recovery, using 47% fewer source accesses than an exhaustive crawler. The closure certificate fires on 93% of schools, meaning the cost reports reflect a policy that chose to stop, not a budget that ran out. On the planning side, DegreeMap maintains 100% exact hard feasibility. It improves personalized utility by 0.066 over the strongest baseline and reduces the average completion horizon from 6.7 to 6.3 terms. That reduction matters because any planner can buy preference satisfaction by stretching graduation out, but DegreeMap does it without sacrificing feasibility. When you isolate each stage, the pattern is clear. Changing the extractor primarily shifts coverage and feasibility. Changing the planner shifts utility. Neither component alone recovers the full system. The end-to-end pipeline certifies 99.5% of planning requests, with a utility gap of only 0.015 relative to a privileged gold curriculum graph. Verifying against the extracted graph would have hidden silent mies extractions. Verifying against the gold graph proves the pipeline's accuracy. KnowPlan removes the acquisition planning circularity by construction. It treats curriculum reconstruction as a standalone, certificate-verified extraction problem, and degree planning as a lexicographic optimization over a typed hypergraph. The framework isn't limited to education. It applies anywhere an agent needs to acquire a world model before an objective scores it against it. Fix the acquisition target before the objective is known. Give acquisition its own terminal condition, and hold out part of the source so goal-driven shortcuts appear as measurable recall loss. If you're working on constraint-heavy planning, knowledge graph construction, or autonomous web agents, this pipeline offers a clean blueprint for separating discovery from optimization. The evaluation protocols are structured to make that interface directly measurable. And in a field where agents often plan over incomplete graphs and hand you confidently wrong schedules, that kind of architectural rigor is exactly what we need.